welcome everyone to this external seminar series. This will be a hybrid meeting. We have some people online as well as physical. For the people online, don't hesitate to put your comment or question in the chat. We might ask you to unmute if you like, or we'll read out loud your question or comment. And also I'd like to point out that we have another presentation on Monday about ultra-processed foods. But for now, I'd like to welcome James, who will introduce our speaker for today.
Hi, thank you, Eddie. So yeah, very pleased. We've got Tabea Sonnenschein here today. We met at one of the conferences in autumn last year, and we've been very impressed with the work she's doing with agent-based modelling for health impact assessment, and it relates a lot to some of the work that we're doing in parallel in the Jive and GLASS project. And there's a lot of exciting methods that Tabea has been generating as part of her studies, and I think she's achieved a great deal, particularly considering this is just part of her PhD work. So I know she'll have an awful lot to get through. I've seen some of these bits before, so I'm sure it's a bit further on. So I'll shut up and over to you.
Thank you so much. So yeah, I first want to thank James for inviting me, and also Jody and Janina for organizing this session. So let me first start. I'm Tabea Sonnenschein. I'm a PhD student at Utrecht University and at the Utrecht University Medical Center in the Netherlands, and I'm part of an environmental epidemiology group, the Institute of Risk Assessment Sciences, but also of a geoscience group and a planetary health group at the hospital. And my research takes place in a pan-European research project called Expanse. And Expanse focuses on exposome-powered tools for healthy urban living. So basically, maybe I should make it smaller. So basically, I'm going to talk about my PhD research, which is on agent-based modeling for urban health impact assessment, particularly for interventions that target the exposome. So maybe for some people that do not yet understand the exposome, it's a fairly new concept. So 90 to 95% of diseases are not caused by only genetic factors, but by either the environmental behavioral factors or an interaction between environment and genetic factors. And so Wild has really coined this term for all these environmental behavioral exposures in 2005 called the exposome. And there's a huge advantage also or relevance of the exposome concept for preventative medicine, because yes, with CRISPR we can change our genome, but it's much easier to change our environment and behavior to prevent diseases. So there's a huge potential. And what is the case is that people increasingly live in cities, right? So we have a rapid urbanization. That means that really this relationship between people and the environmental behavioral exposures is moderated by the dynamics of urban daily life and by urban planning. So this is a really interesting moderating effect that I'm interested in, and it can be also explored for interventions. And so basically, how do you get from scenarios like that with lots of car-based traffic? I experienced it this morning in Cambridge, to be honest, to scenarios like that, which I'm a little bit more used to in Amsterdam, to be honest. But the question is really how, right? It's not so easy to find out. And so basically, my point is that simulation models are basically the only way to test these interventions in advance, because you don't know if you implement urban planning intervention, what will be the side effects, which of the interventions works best, you have a limited amount of budget as a city. And so which ones should you prioritize? And I think for that, we really need a lot of analysis, and simulation models really come in handy here. But apart from just this precautionary benefits of assessing interventions beforehand, there's also efficiency benefits, so that you can basically select the best working intervention. You can also look at how different groups are impacted, so that you make sure there's some kind of a distributional justice. And so my question is always how to basically then effectively predict scenarios of urban exposome interventions. And I'm interested in agent-based modeling, as the title of this presentation already reveals. So maybe to explain the method a little bit, because it's not very commonly used. So agent-based modeling is really a versatile, complex systems method. It starts with having behavioral rules that determine the behavior of the agents, which are basically discrete units. It could be people traveling through a city, it could be cells of an organism, it could be cows on a piece of land. There's all kinds of application. So agents, they have behavior for themselves. They have behavior that determines their interaction with the environment, but also the interaction between each other. So this is the micro level modeling that you do in agent-based modeling. And then these interactions that happen based on the transition functions, they change the properties of the agent or the environment. And that could be any kind of properties. That could be that you have some exposure that an individual is exposed to, or that you have a changing health because of that, or that there's an emission to the environment through a behavior, things like that. And then basically what you end up with is having these micro level behavior rules having effects on the macro level. So you can basically try and model the processes that determine our behavior and environment, and then you end up with public health results. And then you can do scenario modeling. And so basically, agent-based modeling has a set of advantages, and a clear one is that it has this ability to capture complex environment behavior interactions. And that means not just linear relationships that you're able to model with a regression, but also feedback loops and things that, so for example, processes like emergence or adaptation. These are processes that are often studied in complex system sciences. And apart from that, you can really integrate a large amount of factors and nuances. So part of that advantage is that these transition functions, they really can take any mathematical form. So you can plug into this model any other model, and that makes it really, really versatile. You can, any structure of model can be plugged into an agent-based model, and so that's just really powerful from a mathematical perspective. And then last but not least, it's also it can be used as a comprehensive and intuitive communication tool. So because you have you synthesize all the processes that make up the phenomenon that you're interested in, you can also visualize it as a whole and as a dynamic whole, so with spatial temporal changes. And those visualizations can be quite an intuitive form of communicating, especially if you're dealing with policymakers or citizens, and you want to communicate some complex scientific effects of the interventions. I think it's that agent-based modeling really can help as one tool to communicate that. So, but there's of course also another perspective. So here's the devil advocate's perspective on agent-based modeling for this purpose. And I heard it many times. So I heard that, well, it's too complicated or too abstract, that it's unfeasible because we don't really understand the underlying phenomenon. I heard that, yeah, we can't really validate it, or it's too computationally expensive because it's so intricate. Or also that it doesn't really have an added value. So I think these are arguments that need to be heard. and they need to be addressed. They need to be disproven. And basically, that is what I'm trying to do in my PhD partially, because I think that, of course, you can't argue for a method and its universal value. A method has a value in a specific application scenario. So the application that I'm interested in is looking at urban exposome intervention scenarios. So intervention in a city that target these environmental and behavioral exposures that really are so relevant for our health. And in particularly, I'm interested in showing through new methods, tests and applications that, first of all, it's feasible to model urban health intervention scenarios using agent-based model, that one can validate the agent-based model. It is possible, so that because only if you can validate it, then you can use it for policymaking, because anything less would be dangerous, because there would be a false sense of accuracy. And then lastly, I also want to show that there's added value of agent-based modeling over linear models. But I also have to do warning. I'm in 2.5 years into my PhD, and this is very much work in progress. So I'm not done with showing these points, but yeah, I'm on the way to do it. And some of it I have some results already. So as I said before, to understand the value of a method for a specific application, I think it's really important to look at the characteristics of the phenomenon that you're trying to model. And what we're really interested in is the phenomenon of exposure, right? And exposure is basically, if you look down at the sub-processes, it's actually consisting of complex environment and behavior interactions. So I think that there's two types of exposure. On the one hand, you have active exposure, which is basically behavior. You have consumption behavior like smoking, diet, or drugs. You have mobility behavior like physical activity or inactivity. And then on the other hand, you have passive exposure, which is an interaction between environmental stressors that like for example, air pollution or noise or heat that an individual is exposed to at a specific location. And as you can see with all these arrows in this way too complicated graph, there's already some feedback loops alone in that process, right? Because on the one hand, the environment influences our behavioral decisions, and then behavior can also influence the environment. So, for example, by choosing motorized transport, we are the very cause of environmental stresses like air pollution and noise, and then that environment feeds back into our behavioral decision. So there's the behavior choices of individuals depends on the behavior choices of the other people in the city. And so that is, first of all, one theoretical argument for why a modeling of these feedback loops as an agent-based modeling would have some added value over linear models. I will also show later on that, yeah, I can already see that there's some environmental stressors that are behavior determinants for health relevant behavior. So there's already some evidence of these feedback loops that theoretically are there. Next, I have worked on building these agent-based models, and this is basically a model architecture for this type of agent-based models. So the class of agent-based models that looks at urban exposome interventions or like urban health interventions that target environmental and behavioral exposures. On the one hand, you have the environments, which are basically layers of geographic information and can be static or dynamic. You have transport networks, which are important for the individual's routing to the city. You have destinations, which determine where people go for specific activities. And then you have environmental stressor maps like air pollution and noise. And then on the other hand, you have basically a synthetic agent population, which is the fancy word for urban residents or like a population of the city population. And these people, they have a behavior. In particular, we are interested in transport behavior and activity choices. since these are like the most relevant for behavioral exposures and passive exposure. And on the other hand, they have attributes like socio-demographic attributes, but also health attributes. And then there's 3 types of models that determine the interaction between the environment and people. There's the behavioral model, where you have the individual attributes and the environmental attributes causing the individuals in a specific spatial context to make a behavioral decision, like a decision for a mode of transport based on where they have to go and how the environment is, how the individual attributes are. Then the second types of models that you need are the exposure functions and the exposure response functions. So you have to calculate exactly how they're exposed to the environmental stressor maps, which is some more complicated spatial join function, but they're also exposed to their behavior choices. And then you have to link that to exposure response functions or dose response curves. And lastly, there's these environmental stressor models. It's important to model them in a dynamic way because they're dependent on the behavior choice. If you change the transport system of a city, it will not only change the behavior of people, but it will also, through changing behavior, change the environmental stressor maps because they're partially the result of our behavior. And so basically, what I'm going to do in this presentation is walk you through the models for the components that I worked on. And then I will also go a little bit into some preliminary results for intervention scenarios that I worked on. So this is basically a visualization of the agent-based model that I'm working on, just for you to have an idea of how it can look like. You have basically individuals. They have a home and they're representative for their street block, and then they're making they're traveling to their destinations, making decisions, being exposed, etc. And you can aggregate it over time, and then you can make all kinds of conclusions. So let me start with the synthetic agent population. So there's the following challenge in agent-based modeling, which is that usually people take individual level data of sample of individuals, and then they multiply it to have a full representative data set of the population. But you don't have this data everywhere. Like, you don't have individual level data available. I didn't. So but I still want to have also a representative population where the attributes correlation is also representative. So because, you know, people that have this attribute and this attribute are more likely to have this attribute. It's not independent, right? And I also want this population to be spatially representative, because a city is not necessarily, like, it's not equally distributed with the same type of population. So basically what I do is I combine 2 methods. One is called synthetic reconstruction, where you basically calculate conditional propensities to have an attribute based on multi-joined variable distributions. And that means that you take stratified data where you have, for example, that is publicly available through census data. You have publicly available what is the number of people that have this level of education based on migration background, sex, age. And then you have propensities to have this attribute, and you can distribute the attributes accordingly. And then the second method that I use is called deterministic reweighting. And for that, you basically have marginal distributions across spatial units of the attributes. So basically, for Amsterdam, I'm really, really lucky that there's data available on the street block level, which is really spatially detailed. And basically, I can use this, you combine these 2 methods to create an individual level representative population for Amsterdam, and you can iteratively add more variables. And that means that if you add more variables, you can use all these variables as conditional variables so you can make it more and more robust. And but it depends on what you have available as data. So if you don't have as much data available, then you can still use that method with whatever data you have available. And to make it reusable, I also developed an R package called GenSimPop. You can download it. There's also a paper that's going to be published soon. And yeah, basically what I did, I collected data on demographics, socioeconomics, health, and behavior. And okay, moving on to the most complicated part of the model, because basically, yeah, what I think is the most challenging is modeling the behavior, because we're really complex beings and we're so diverse and our decision making is so diverse. So there's multiple disciplines really trying to figure out the issue of behavior. And then you just have to model a whole population of it in a city. And I felt really overwhelmed with this task. And I also really wondered, like, how can I build a valid behavioral model? Because yes, you can model something, you can collect some empirical data, put some variables in and have a predictive model. But if I want it to be usable by policymakers, I really have to prove that this model is valid. So that task kind of pushed me into a philosophical discussion about what validation meant. And basically, there's some interesting work from Alman that shows that in a simulation model, validation means substantiating that the behavior of the model represents the behavior of the system with sufficient accuracy. And you validly mentioned that, yeah, it's a bit difficult to define what is sufficient accuracy. But what is interesting is that there's two different types of validation. And there's replicative validation, which most people just know as calibration. It's you basically calibrate the parameters of a model based on data, and you cross-compare it to a different data set. And it's replicative means the model can replicate the results of that you're observing. But this is different than structural validation, because what can happen is that you have, for example, confounding variables that completely mess up the weighting and coefficients that are actually the causal determinants of a model. So structural validation means that ensures that the model is generating the correct input-output behavior for the right reasons, and not because of incorrect behavior of one model component compensating the incorrect behavior of another model component. And so the structural validity is something that really bothered me, and especially because it's not really done in a lot of simulation work. People don't they do some tests for replicative validation, but structural validation is ignored. So that is problematic, because if you miss a confounding variable or important interactions or moderating effects, you can drastically misestimate like hypothetical scenario effects. So that's why, yeah, I was trying to think about how can you actually structurally validate a model. There's two ways to actually get to truth in some way. You can have just a test, a data-driven test. But another way to actually to get to a conclusion is using existing sources of valid knowledge. So that is I think the most feasible way of doing structural model validation, because you have valid variable selection methods like lasso, elastic net, etc., but they require you to have already a set of variables to put into that model, and it's really inefficient. Like how do you first of all, it's really arbitrary which variables you put into this data-driven variable selection method, and then it could be also inefficient because you could put a lot of variables that are not relevant. So what is already out there is a lot of behavioral evidence, for example, and so I thought that systematic reviews and meta-analysis are a really good source to inform the variable selection, the type of relationship that you want to put in. But I was also then really a little bit overwhelmed with how vast the literature is, and also with how difficult it is and time consuming to really read all of this systematically. So doing a systematic literature review or meta-analysis just takes time. So that's why I thought, yeah, maybe it would make sense to automate this process so that you basically can do it for every model component, because otherwise it would just take forever. And so that's how I then decided to start with the method. I first looked at what is the information that you want to extract. You have basically in causal theory, you have the independent variable, you have the dependent variables, and you have associations, and you have a sample for which that you test the relationships, and then you can have also moderators. And so basically that's I applied that to behavioral science, and what I'm interested in is the behavior choice option. Let's say for mode of transport, that could be walking, biking, etc. Then you have behavior determinants, that could be income, that could be the amount of green space around. And then you have the study groups that say, like, yeah, okay, some studies just focus on children, some studies just focus on parents, and etc. That's a sample. And then you can have moderators and information the study. And so basically, I transformed them into labels, and then labeled a subset of articles with this information. Because if you actually read a sentence in an article that contains evidence, it's usually structured as such that you have the dependent variable, like a behavior option. You have the independent variable, like the determinant, and the association type. And sometimes you have information on the study group, sometimes the information is in the title of the paper. And so it's actually all encoded in language in our articles. And so what I did is I used BERT, which is a transformer-based, pre-trained natural language processing model. And I used it for named entity recognition. Named entity recognition means you have tags, and the model learns how to find when to apply these tags to words in the sentences. And actually you don't need to like manually label a lot of articles, because it's already pre-trained on language. So for example, ChatGPT is based on the same transformer model as BERT. And then basically it's doing a really good job. As you can see, I've a weighted F1 score on the validation sample of 0.87. Anyway, then you have labeled this the information that you want to extract from these articles. Then you have to put them in relationship to each other. So you want to, because there's sometimes multiple evidence instances, that you want to have each evidence instance that I want to extract. And for that, I basically use I use the syntactic properties of the sentences. So you can add them as features. I basically combine all possible combinations of phrases in a sentence, and then I add the syntactic properties and train another machine learning model to do the prediction. It's again doing a really good job. And then basically you have to deal with the issue of having multiple variable names for the same. So that's the knowledge synthesis issue. Also, if you're manually reading it, it's kind of problematic. So what I'm doing is I use the string similarity and the semantic similarity. So there's really nice work from WordNet, which is an open source semantic network of where words are closer in the network if they're like more synonymous. And they have also some really nice packages in Python with where you can find synonymous words of a word. So I use these packages to then do some variable harmonization. Because of time, let me just skip the results, but it's doing a fairly good job. And then in the end, you have like knowledge graphs of the phenomenon that you're trying to model. And you can use this information to inform the structure of your model. And these are just simplified graphs. But basically, what I then did is I implemented the model as well. So, for example, I find that there's 124 consistently significant variables for the mode of transport options that I'm interested in. I'm interested in walking, driving, biking, public transport for now. Just trying to keep it simple first. And so I found that I have 80 data for 80 of these variables. And because some of these variables are still synonymous and can be grouped, it's 43 distinct observations. And then I have Odin microdata, which is the Dutch transport survey, where you have information of postcode level origin and destination with all kinds of attributes of the population and also the purpose of the trip, etc. And it's really representative. So I join it to the environmental and data and I use the individual information from the survey for the individual variables to then build this mode of transport model. I also know from having extracted the data, I know that I'm missing relevant variables on psychosocial variables, like the social network, social norms, etc. I don't have measured data on that. I know that I'm missing data on aesthetics, vandalism, some very specific amenities like public toilets and easy access of building entrance, etc. But that's okay. I will address it as a limitation, and I know that this is a limitation. And so basically, I have these 80 variables, and then I build a decision tree models. I actually want to also assess what's the added value of having extracted this knowledge. So I actually group the variables into frequently studied variables, semi-frequently studied variables, and infrequently studied variables. And then I train decision tree models with these subsets. So one with just the frequently studied variables, and we see here that the validation weighted F1 score. So for a classification problem, weighted F1 score is a really good performance metric. It takes precision and recall into account. And so we have a 0.5 performance. If you take frequently studied and semi-frequently studies, it's actually variables. I mean, it's not gaining that much. But if you include all the infrequently studied variables as well into the model, you suddenly have a performance of 0.72, which is really good for a behavioral model. So I tested this with 10-fold cross-validation. But here's another chart where you have basically the frequency of study for the variables and the variable importance. And you see that a lot of unfrequently studied variables are actually really important. And this is the variable importance from the decision tree. And let me also come back to the point of the feedback loops that I made in the beginning. You see that noise on the day and night is quite an important behavior determinant for mode of transport. So there we go with we cause noise through our mode of transport choice, and it causes our mode of transport choice. This is again evidence for a feedback loop. But moving on to the other components. So you have, of course, other types of behavior, routing behavior. So the ones they have made a decision, they also have to choose the route. I did a simplified assumption of that they will choose the shortest path. Of course, there could be different routes, but actually in the Netherlands, the quality of the roads is more homogeneous than in the UK. So it's a safer assumption to make there than here, I assume. But still, I use the open source routing machine. One doesn't have to reinvent the wheel when unnecessary. So, and then you have activity. So for the activity choices, I have the HETUS data harmonized European time use survey, where you have 10 minutes and time step information on activity choices of a representative population across Europe. So you can use that data. Unfortunately, the last survey was in 2010. So waiting for the new data, but so I'm using the 2010 data, which is probably not 100% representative, but they have schedules based on their social characteristics. I'm not having a dynamic activity choice because, I first test transport intervention. And then based on the activities, they choose destinations. So basically, if they go grocery shopping, they're gonna go to the closest supermarket. If they're going to the school, they're going to a school, or if they go to just shopping, they'll choose one of the services destinations. I use Foursquare, which is a place-based social media, but they have actually really good points of interest data because they employ some people to keep it up to date. And so basically it's just an example of how the people route through the city. There's some ferries here, don't be confused. Yeah, moving on to the exposure functions and exposure response functions. So there's a bit of an issue, which is that the exposome science is a fairly new field. The term was coined in 2005, as I said. And so the exact pathways of exposures leading to diseases are not fully understood. For some exposures, yes, but there's an issue of having correlating or co-occurring exposures, right? Like noise and air pollution and heat and stuff like that. And so basically another issue is that the empirical studies on exposure effects are usually based on yearly average, because people are really happy to have matured birth cohorts or just cohorts in general, large cohorts enough to do a data analysis. And then usually also in my epi group, what happens is that you join it with the yearly average air pollution at the home address. So basically they don't take human mobility into account. So basically how the exposure is estimated in the majority of the environmental epidemiology field is different to how we are modeling it. So we are trying to go to personal exposure level, which is taking basically the spatiotemporal mobility into account. We can also take the spatiotemporal variation of the environmental stressors into account. So because there's differences between day and night, and also between seasons very much. And so there's also differences with behavior across day and night and season. So actually if you take this variation into account, you end up with different estimations of the exposure. So the question is, how do we then model the response when the evidence that we have is based on different estimations? It's still an issue. I would say just aggregate the exposures to a level for which the evidence exists. So that would be like, maybe a year for chronic effects or something like that. It's something that still needs to be worked on. But there is some studies now in environmental epidemiology, also in the program. Actually, in Exposome, they have this urban labs where the studied participants are equipped with all kinds of sensors and patches and trackers, and so they're really trying, and they fill out like also time activity surveys and everything. So they're trying to really bring it down to the personal exposure level as well, but it's not as large of a sample size, so there's like different types of analysis that you can do. And so then basically what is the case? As I said, the exposure is basically a more complex spatial join. You have like the tracks of people's mobility track, and then you take you have a raster of the environmental stressor, just a raster grid of the environmental stressor value, and you see like if they're spending more time in one cell, then they're proportionately more exposed to that cell than another cell. And you could add more things. For example, since the activity that they're doing, if they're doing active transport or they're doing passive transport, you could take inhalation rate into account. You have individual level information. You could take the tidal volume into account based on age and BMI, etc. But these are just like more heterogeneous exposure response possibilities. So the evidence basically that is safe to use on the aggregate level are the global burden of disease estimates, and you could basically aggregate it to those yearly exposures and link it to these. And because it's so not yet on that level of that we're modeling it, I think it makes sense to use more aggregate metrics like DALYs and mortality and etc. And yeah, I haven't implemented that yet. But then looking at the environmental stressor models, oh, I have to hurry. What I'm doing is you have the issue of deterministic physical models taking hours and hours to run for a single hour computation of like, for example, atmospheric dispersion. But what I'm trying to do is I try to solve this issue by basically joining land use regression model for on the streets with an off-road cellular automata-based diffusion model. And the on-road model is based on actually mobile measurements of Jurij-Kerkhoff and Zhendong Yuan. And so that the cellular automata model is basically works as such that you have a cellular automata means that you take the neighborhood values into account to compute the center value. And what I do is I define a moving window, and it's based on the wind speed, rain, and temperature. So the moving window is weighted depending on where the wind is coming from, how strong the wind is. So the disparity from the place where the wind is coming from and where it's going is larger when the wind speed is larger. And also the propagation rate is dependent. And then there's an adjustment for like through this iterative process of cellular automata. It's just a few iterations, actually just 7 iterations. There is some adjustment for the morphology. So the building heights, the fraction of open space and number of trees, etc. And basically, this is just some explanation of the moving window, which is a bit more complicated. You basically, so you have in a wind direction, you have a 360-degree indication of where the wind is coming from. And then, these places are weighted more than where the wind is going, right? So, and I basically segment the 360 degrees in 16 segments, because that's what I'm able to model. And then they all have a 22.5 degree range. And then basically you have the direct wind direction cells and you have the neighboring cells. So, and then there's a propagation rate. That's just a general propagation rate dependent on the temperature and rain. So how well does nitrogen dioxide go from one cell to another cell? That is calibrated based on some weighted temperature and rain. And then you have the disparity factor, as I said, which is dependent on the wind speed. And then the disparity factor 2 is a fraction of the other disparity factor. And where the wind is coming from is the propagation rate times the disparity factor. Where it's going, it's basically divided by the disparity factor. So, and all of these parameters have been calibrated using genetic algorithms. So basically, here I use palm tubes, which are 155 stations. So yeah, it's unfortunately measurement data is not that great for evolution, especially temporally varying. But so these palm tubes, they have been used for the calibration, and then with the external validation, I used hourly RIVM off-street measurements. Both of them are off-street, right? Because we're interested in the off-street dispersion. And actually there's an R-square of 0.6 for predicting this external data set of off-street with the hourly variation. So it's actually not so easy to predict hourly variation with meteorological seasonal changes off-street. So it's okay, but it can get better. So basically the idea is to improve it by maybe making smaller spatial units. And I'm also working with Gibran and Zhendong to compute some other morphological dispersion moderators like the frontal area index and sky factor, but then these are like more complicated. So basically what I did is I'm trying to build this toolbox for agent-based modeling. You saw the genetic synthetic, generation of synthetic population package, the knowledge extraction package, which I made actually also into a Python package, and then the cellular automata dispersion, which is this hybrid land use and cellular automata model. I'm also transforming into an R package right now. So just quickly before I end, looking at the intervention scenarios, this beautiful cover, the critical mass book. I'm not done with this intervention work. So what I first tried again, because I'm so obsessed with this question of validity, because I was so scared that in the end of my PhD, I'm going to stand in front of a panel, show my agent-based modeling, and they say, it's not valid, or it's not usable, or something like that. And I really want to have some results. So what I tried to do is basically take an existing intervention that has been done in Amsterdam, which is actually in 2019, there was a parking price increase of 66%. And what is really nice is that there is an urban economic study on it, where they actually estimated based on the parking data and traffic volume data, which is different data than I use for my behavioral model. And they estimated the impact on the traffic volume. So basically, I use that. And then I test my decision tree model with data. I trained it from data from before, and I test the mode of transport change with the new parking prices of afterwards. And it's interesting because I first looked at the overall city, and I said, oh, it's just 3%, so the model's really bad. But then I looked at the area that was actually studied in this model, which is just the small area where the parking prices changed. And then I realized, oh, wow, yeah, it's actually really similar to what so that gives some validity to the behavior model again. Oops. And you can also see, yeah, it's, this is not actually that informative. I have to still improve the visualization. But I'm now that I have this behavior model, I can also look at other scenarios. I'm still working on the intervention modeling. I'm looking at different transport interventions, but I don't really have anything to show on that yet, other than this. But what you can do is, you can test different scenarios. So what I did, because trip distance was the biggest factor, and you can influence trip distance. I don't know if you heard about this concept of the 15-minute city, where you have everything in really close distance to like all of the destinations. So what I did is a hypothetical reduction of like the original trip distance. So if you reduce it to 95% of the original, to 90%, 85% of the original, what is the change of the mode of transport? And it's interesting because yeah, so biking stays pretty constant, and at some point, if you reduce it by like by 30% or even more, 35%, then suddenly like biking also walking also replaces the biking, which makes sense. But yeah, so that's just some preliminary results. But yeah, I really need to work on quite a lot of components. I'm interested in testing the speed limits and maybe some like temporary parking, replacing the parking spaces with some temporary gardens or green spaces, looking more and more active transport infrastructure where the Netherlands already is really good, but there's still some deficient areas. And yeah, I have to work on some of the components. But yeah, I want to go back to the devil's advocate in the end. And I want to say that, yes, it's complicated, but what you can do is you can compartmentalize the phenomenon. You can look at specific behaviors, you can look at specific environmental processes, specific health impacts, and then you can modularize it so that maybe others can reuse it, and then we can collaborate across different research units and cross-validate each other, criticize each other. Then you can use data for calibration and cross-validation, and you can use previous literature to validate each component on its own. And then you can model existing interventions with data from before to test, if the whole model as a whole is valid. So you can validate it. And there's computational solutions to the computational costs, such as, for example, doing a hybrid cellular automata model versus just doing a linear land use regression model, or just a deterministic model. So famously, Box wrote in 1979, all models are wrong, but some are useful. So this question of the usefulness of agent-based modeling is still an open question. I'm still trying to test that. Also, so for example, I'm planning to compare the ABM scenario with linear health impact assessments scenario to see like what's the difference, where is it getting better at, and And I have this dream that at some point, you know, you can have some interactive agent-based modeling for policy making, so that it has some really real world value for policymakers. I want to acknowledge my supervisors, Simon, Ardina, and Roel van Merle, and my mentors, Nicole Brava and Catherine Ton, and my air pollution model collaborators, and then Yuan and Gibran Khan, and of course my computer, which is my most dear partner. Without it, I would not succeed. Okay, thank you so much.